Hi, I'm Brad Booth. I'm the Principal Network Architect with Microsoft Azure. I'm also the President of the Consortium for Onboard Optics, also known as COBO. Here to talk to you today about optics. We are obviously seeing a massive change in how we look at using optics in our data centers going forward. If you take a look at how our data centers are built today, you will see that our network infrastructure is actually bifurcated. We have a very large portion of connectivity that is actually electrical. Even though we use active optical cables, the connection for them are actually electrical. We don't have any exposed optical connectors on those connections. So really, it doesn't look radically different for that AOC than it does for our DACs. And the direct attached copper cables and the AOC's active optical cables are the largest volume deployment connectivity that we have in our data centers. It isn't really until we leave the rows or our clusters that we actually start using optics. Now, in the case of Microsoft, we use a lot of parallel single mode fiber, 100 gig parallel single mode fiber. Eventually, we will move towards 400 gig DR4. When we build these data centers and we look at doing the deployment, all these connections into these optical modules or into the DACs or into the AOCs, a lot of those connections are electrical connections. So even though we have these optical connectors out there that we're using, the volume of optics that we actually deal with is fairly small in a data center. When you look at the electrical connectivity, there's a big push right now for 100 gig PAM4 signaling, electrical signaling. There's already conversations going on about 200 gig PAM4. But one of the things that's most noticeable when you take a look at the 100 gig electrical signaling, whether you use 7 nanometer process node or a 5 nanometer process node, the curves basically follow the same trend lines. And what we're seeing is that you get this transition every time you have to bring in extra circuitry to compensate for noise or impairments in the electrical connection. Those, every time you have to compensate for greater and greater noise, it starts costing you more and more power. So for example, when we do extremely short reach, XSR type connectivity, we can keep the power down fairly significantly. When we start looking at what most switch silicon uses today, and it's LR type SerDes, long reach type SerDes. And the primary reason why they use that long reach SerDes is because they're expecting to drive a direct attached copper cable, a DAC cable. If you were using optics, you wouldn't need to have a long reach SerDes. If you only had optics on the faceplate, you would use a VSR SerDes. That was one of the things that we discovered when we did our specification, our onboard optics specification as part of COBO. We realized that you could build these optical modules and you could do it in such a manner that you didn't have to drive, you wouldn't use a DAC cable, you would only talk to optics. And in that case, you could use a VSR, a very short reach type SerDes. So what we're seeing though is as the industry keeps pushing and pushing on the speed, the electrical speed, this power is actually not continuing to come down. The power we paid picojoule per bit at 25 gig versus 50 gig and then to 100 gig and 200 gig. It's not a linear curve straight down. It actually is a curve that's starting to flatten out. So in other words, as we're increasing in speed, as we keep trying to push the technology, we're starting to pay more and more power. And that power comes from things like the DSPs or the number of equalizers that are required to actually make these work. And the reason why this is important is that when we build these systems, when we build our data centers, power is our basically our currency. How we build them, we have constraints on how much power we can draw. So if I build a data center for 100 gig today, and say it's 60 megawatts, for example, and say we're drawing all 60 megawatts from the supplier, when I want to retrofit that or outfit that same data center with 400 gig, If there's not a power savings, or in other words, if the same power per bit is the same at 400 gig as it is at 100 gig, that means I have quarter the size of the network I can deploy. So we have to be cognizant of how much power is being burned by our network. And what we're seeing is over time, that power is increasing. Where our network power used to be maybe 5 to 7% of a data center, it's starting to increase past 10%. And it may not seem like it's significant, but that's power that we can't put towards our applications, or that power gets burned up by the network. And therefore, for me to be able to have the ability to take on new customers, I have to actually consider building a new data center. So there's a lot of cost implications here as we start burning through power. So some of the challenges that we're facing going forward, especially when we start looking at how do we bring optics in, and optics themselves are, been around for hundreds of years. We're not hundreds, but 100 years at least. What we're seeing, though, is optics has this mentality of total cost of ownership. Optics are not cheap. They have been fairly expensive. They're expensive to use. They're expensive to deploy. It's a bit of a stigma that sits with the optical modules in the industry. And so we have to figure out, how does that work within our systems? How do we make sure that we can balance this out so that it becomes a easy enough transition while keeping the total cost in control? The other aspect of this that we're finding with optics is, especially when we want to look at how do we drive tighter and tighter integration, is the manufacturing. So for example, today, it's well understood that when you buy an optical module, you buy that from one vendor. That comes as a single component. You take that and you plug it into a switch that you bought from another vendor. Now, sometimes there's vertical stacking. Sometimes the vendors that build the switches also build optical modules. That's fine. But you have this capability of exchanging those parts, and that's well understood in our industry today. The other aspect that kind of gets in there is, when we look at it, is trying to drive change. And optics themselves are fairly easy to build, fairly easy to understand and manufacture. And, we are creating new things and new technology all the time. But the real hard part is to get people over the mindset, the hurdle of, I'm going to put optics in. Because optics are not perceived also to be nearly as reliable as a passive direct attached copper cable. So we have to deal with that as we progress forward. So what we can see when we start looking at total cost of ownership, you can actually tell when you do the cost comparison, DAC is quite affordable. That being our baseline, our AOCs are about 4 times the cost of a DAC. When I go to optics, that jumps up to 16x. That's a huge cost difference. Now, predominantly, the optics that I'm using, that's that 16x, is my 100 gig PSM4. The ones that are being used at the AOCs today are typically VCSEL-based designs. So there is room to change that cost equation. The other aspect that comes into play in this total cost of ownership is not just how much money you put out of pocket, but also how much does it cost to operate. And one of the trends that we're starting to see is, if I am building my optical modules in the same way that I build a DAC, in other words, I plug it into the faceplate, I'm going to always be paying that power penalty. Because if I am using DACs on that same switch port, I have to be able to power it. That's how we think of it in the industry. So one of the ways to do this is to change your mind mentally and say, okay, I'm going to integrate the optics. And therefore, I don't need an LR SerDes channel. I don't even need a VSR SerDes channel. I can maybe use an XSR SerDes channel, something that's much closer to the optics and drives a lot of the power out of these systems. And that's actually one of the things that we've noticed, is that if you look at sort of the Gen 1 timeframe, we're seeing that power almost half of what we use today for pluggables. And Gen 2 even drops that even further. All of this means, though, that when we take a look at total cost of ownership, it's not an easy assessment to do, because some of this is based upon implementation design. Some of this is based on future-looking technologies. Some of the things change as we manufacture and design and build these systems. The other thing that gets interesting when we look at the manufacturing is who does what. When I look at an integration, like I said, you have a module that sits on a faceplate that you plug into a switch. Switch has an ASIC inside and all fairly easy to understand. But when you start doing the integration, you start changing the players that are involved in the story. So where before you may have bought an optical module from an optical module vendor, and you may have bought a switch from a switch vendor, now you're looking at it from the point of view of who built the ASIC, who built that optical engine, who's putting that whole thing together. How do I make sure it's manufacturable? How do I make sure it's reliable? How do I handle yield problems? What happens if I have a failure? How does that get serviced? So co-packaged optics is definitely changing how we view this. But that tighter integration is giving us a value. And part of looking at this, and the reason why we need to start early, is we need to figure out these things. The industry in general is moving very heavily towards integrating photonics and electronics. And because of that, we need to figure out how that changes our deployment models, how it changes our serviceability models, how do we handle reliability? What happens if there's a failure? How do we service that? These are all things that we have to figure out, and it just takes time to do so. So while change is hard, and yes, this is one of my dogs, and the reason why I use this picture is because I love the term, let sleeping dogs lie. And it's true. It's very easy for data center operators and others in the industry to continue down the same path we've had for forever, for quite a long time now. And that it makes it hard to mentally bring yourself to say, hey, I'm going to bring out something that's going to change things. I am going to have to change how you service things and all this other stuff. I'm going to potentially impact how we look at reliability. When you start bringing those things in front of IT professionals or data center operators, you immediately get a lot of apprehension. It's like, oh my goodness, you're not going to break anything, are you? And that is the harder problem to answer for a lot of us. We don't really know. Our goal, of course, is to offer better reliability, better manufacturability, better cost models than what we do today. But that change takes time, and change is hard. And so it's much easier to sit there and continue to do the things that waste power, that cause us to deal with thermal environments that are, quite honestly, pretty insane. If you look at a switch right now at 400 gig, if you've got 15 watts on a module and you populate 32 of them across the faceplate, you're dealing with a significant amount of power right there. And when you look towards 800 gig and 1.6 terabit, do you honestly think that we're going to be able to handle that type of thermal load with faceplate pluggable optics? We know we're going to have to figure out new ways of doing this. And yes, we can bring in new ways of cooling, do immersion technologies, whatever. But we still need to solve that problem, because the reason why we're creating that heat is because we're burning power for no good reason. The other aspect is we don't know what we don't know. So there's a lot of questions still going on. What will this look like? What happens when we start integrating optics and electronics? This whole photonic electronic integration, what does that mean? When does that happen? And that's where the standards bodies are trying to do some work. And there's a lot of companies in the industry that are investing time and investing money. You can even look towards, the U.S. Department of Defense and the DARPA project, the PIPES project. There's a lot of work going on to figure out this problem. How do we solve it? One, scope out the problem. Two, figure out how we can solve it and manufacture it. And it's nice to see that we as an industry are progressing on this. We understand that this pain point exists and that it's going to happen. And that is a lot of where the things that are occurring in this industry is happening now. So while optics, as I said, are easy, the change is hard. And that change will take time. So, we may be able to create these solutions to have them manufactured in volume and deployed in volume is going to take time. But that's where we as an industry have to be patient, because we know that this is the right thing to do, that we have to save power, we have to do better designs, and we have to be smarter in how we build these. Thank you.